Hello, thanks for joining us. My name is Fernandez, and I'll present work done together with Professor Plumbley at the Center for Vision, Speech and Signal Processing at the University of Surrey. The work is entitled Using UMAP to Inspect Audio Data for Unsupervised Anomaly Detection under Domain Shift Conditions. First, we will introduce the task, problem motivation, and proposed contribution. Then we will review our methodology and some results. Finally, we will reach a discussion and conclusion. The task of unsupervised anomaly detection arises when there is limited knowledge about the anomalies, that is, when usually only normal data is known beforehand. This is commonly depicted as normal data being distributed around a specific mode and then the anomalies being distributed farther away from that mode. If we can then find a tight boundary around the normal data, we classify anything outside of that boundary as an anomaly. In the context of audio, UAD is a promising technique for predictive maintenance of industrial machines. But there are some challenges. For instance, sounds may overlap, leading to contamination, and anomalies may be given by short sounds or large sequences, which usually implies having high dimensionality. UAD under domain shift conditions has the added difficulty that normal and anomalous data can be exposed to potentially unknown changes. For instance, on the left-hand side, we see a boundary that might be valid for a specific domain, but if we apply that same boundary on a shifted domain, that might lead to false positives and false negatives, reducing the quality of the detection. The DCASE challenge has featured UAD and UADS tasks on the 2020 and 2021 editions, respectively. The 2020 edition featured a dataset with several devices that were recorded functioning normally. Those devices were then intentionally damaged in order to gather anomaly evaluation data. The evaluation was performed with AOC and PAOC metrics that measure the discrimination ability of the models. A variety of deep learning related models achieved scores above 90%. The 2021 edition featured a larger dataset with a target domain featuring circa 0.3% of training data. This means that a large majority of the training data is on the source domain, so the models were forced to adapt to the target domain with very little information. Results in this edition were drastically lower. The winners achieved a score of 66.8%. So the question is, why were the scores in 2021 much lower than 2020? Several trends in the literature hint at the task difficulty independently of the approach and at the relevance of the data representation. So our plan is to visually inspect that data. Specifically, our proposed contributions are: we present a methodology and software that uses UMAP projections to visualize audio data and to look for separability and discriminative support. We present insights on micro and macrostructure of the 2021 dataset. We also formulate a set of verifiable hypotheses with the hope that they will help directing future efforts in the field. In order to visualize high-dimensional audio data, we need to project it down. For that, we use UMAP, which is a scalable, stable, and meaningful projection technique with many mathematical guarantees. For our work, we operate with one main assumption. That is, if two regions appear separable on the projection, they are also separable in the original domain. For instance, on the left-hand side, we see that the two-dimensional data that is being projected onto one dimension results in two separable regions. So we infer that the original data is also separable. But note that the converse is not necessarily true. For instance, these two projections appear to be mixed, but in fact they have clearly separable boundaries. So based on our main assumption, we propose to look for two beneficial visual qualities: separability and discriminative support. Separability happens when there is a simple boundary that separates normal and anomalous data, as we have seen. Discriminative support happens when training data covers normal data, but not anomalous data. That way we can use the tight boundary around the training data to discriminate between normal and anomalies. The picture in the slide illustrates this. On the left-hand side, we see the training data and the normal data. And on the right hand side, we see the exact same training data, but only with the anomalies. So region 1 provides a decision boundary that is able to separate a patch of normal data from a patch of anomalies, therefore having good separability. Furthermore, the training data covers the normals, but it doesn't cover the anomalies. So it also provides discriminative support. That is the ideal scenario we are looking for. On the contrary, region 2 appears completely mixed, so it lacks separability and discriminative support, and region 3 has good separability but bad discriminative support. In order to inspect the full dataset, we render circa 200 plots covering the global, per device, and per split regions. We also observe 3 different representations that are popular in the audio community: log STFT spectrograms, log MEL spectrograms, and L3 embeddings. The following 3 slides illustrate the global, per device, and per section plots with some of the structural trends that we have observed, and readers are invited to discuss at the poster session. Based on our observations and analysis of the literature, we propose the following hypotheses. First one is that mixing toy Atmos and MIMI may hinder UADS performance. Second hypothesis is that temporal context and pre-training regulate a trade-off between separability and discriminative support. The third hypothesis is that normalization is a dominating factor for this dataset and task. Fourth hypothesis is that incorporating domain-related priors may help performance. To the best of our knowledge, none of the participants have made use of this information. We also present some shortcomings from our methodology and possible ways to address them. There are shortcomings related to projecting and subsampling and also stacking the data, which relate to computational limitations of the setup. There are also shortcomings related to the qualitative visual evaluation of the data, mostly perceptual biases. So in conclusion, we presented a methodology and software tool for UADS analysis. We revealed some properties of the dataset, and we proposed verifiable hypotheses based on the plots and literature. For future work, we propose to incorporate further representations and temporal relations. We propose to enhance the kind of plots with sonification and highlighting, and to extend the technique to supervised scenarios. Feel free to check the link for our resources, which have been released under liberal licenses, and come to our poster session for further discussion. Thank you very much.